One of the problems with living on a planet is our lives and the behaviors of our world are directly linked. If Mars Curiosity was sending back data on a massive dust storm that was buffeting its systems while its nuclear power system let it send back data, I'd gleefully be discussing that terrible weather. Whenever Jupiter gains or loses magnificent spots, that is news. And we are here for that news. But when it comes to Earth having record breaking storms, record breaking air temperatures, and record breaking ocean temperatures, there are weeks I look at our planet's science and just nope out and decide I'd rather cover science that has less of a direct impact on my life. But our human tendency to just turn away when the bad news gets too extreme is part of how we got here. Scientists have been shouting since the late 1990s about climate change, with papers coming out in the early 2000s that described potentially catastrophic effects that we'd see by 2100. It was easy for folks to say, nah, it can't possibly get that bad, as they turned away from the data. It remains easy for folks who don't have the bills to worry about, who aren't faced with paying high heating, high cooling, or high water bills. It's easy for those people to continue to look away. But, and there's always another but here we are, 23% of the way from the year 2001 to 2100. And people around the world are dealing with droughts, flooding, storms, heat, and famine. No one is writing press releases to discuss the death tolls, and the nightly news is largely filled with other news. But here at Escape Velocity Space News, we need to take a look at our planet. In this episode, we need to take one of our periodic looks at the science of Earth and understand what this science means to life as we know it. But we're only going to look at Earth for the first two segments, for the first half of the show. Then we're going to race away to enjoy an interview by Beth Johnson with Dr. Kat Volk about the icy Trans-Neptunian objects that fill the spaces around Neptune and out beyond Pluto. In our final segment, we're going to look at all the amazing and, in one case, alarming launch attempts of the past 2 weeks. It's a lot. We hope you'll stay for all of it. All of this and more is coming to you right here on Escape Velocity Space News. I am your host, Dr. Pamela Gay, and I am here to put science in your brain. On June 1, a lot of different things happened. Personally, I looked at my garden and realized it is probably too late to plant peas. But that's a me problem. At the national level, meteorologists everywhere took a moment to remind us that the 2023 hurricane season has officially started. Current models from the U.S. National Oceanic and Atmospheric Administration predict between 12 to 17 named storms will spin through the Atlantic, with 5 to 9 of these storms becoming major hurricanes with sustained winds over 110 miles per hour and a category of 3 or greater. This isn't a certain thing, and different models make different predictions. The UK Meteorological Office predicts 20 named storms with a higher number of major hurricanes, and the University of Pennsylvania spans the range, predicting 12 to 20 named storms. The U.S. model from NOAA looks at a variety of factors such as the current ocean surface temperatures and the forecast for the West African monsoon season, which are currently at odds with one another. The extremely warm ocean, it's an El Nino season. It generally means fewer storms get started, while a more active monsoon season usually means more storms get started. So, an average year seems likely. However, many storms do actually form. Those ocean temperatures are concerning. Hurricanes are powered by ocean heat, and a warmer ocean means more energy available for storms and the potential for powerful storms to develop. Currently, weather forecasts focus on what we can expect over the next 5 days, but it has become increasingly clear that just isn't good enough. According to NOAA Administrator Rick Spinrad, quote, "This year we are operationalizing a new hurricane forecast model and extending the tropical cyclone outlook graphic from 5 to 7 days, which will provide emergency managers and communities with more time to prepare for storms." End quote. Powering these improvements is a 20% increase in NOAA's computing capability, a new hurricane analysis and forecast system, and an upgrade to their storm surge models. While NOAA is doing all they can to make sure emergency managers have time to prepare for storms, we'd like to remind you that we all have to work together to keep ourselves and our households safe. If you are living in a hurricane-prone region, now is the time to make sure that you have a go bag put together with needed medications, important documents, and the basics you'll need to get by. Have a plan on where you'll go if you have to evacuate. And don't forget to include your pets in your planning. Have a doggo that is car challenged? Make sure you have a carrier. It is often possible to get free or low-cost kennels through your local shelter, vet, or Buy Nothing group. Humans aren't always good at heeding warnings. If you need a reminder of just how warm oceans power storms, the Western Pacific Ocean has you covered. On May 20th, a tropical depression formed north of Papua New Guinea and began a journey north and west. Growing to the equivalent of a Category 5 hurricane, this storm began to buffet Guam on May 22nd and eventually crossed over the island on May 24th. President Biden has declared Guam a major disaster area, and while no deaths or major injuries have been reported, water, power, and other critical infrastructure has been ravaged by the storm. The storm skirted past the Philippines, Taiwan, and Japan without making direct landfall, but still caused damage. Multiple buildings collapsed on the Philippines' Cagayan Island. Luckily, as the storm headed north to skirt Taiwan, it significantly decreased in strength, and when Mawar made landfall on Okinawa on June 1, it was only a tropical storm. At the time of this recording, we're still waiting to hear how the rest of Japan has fared, but significant damage is not expected. This storm is the third named storm of the Pacific hurricane season, and with winds gusting to 210 miles per hour, it was one of the top 5 most powerful Pacific typhoons to occur in May. I often say that astronomy advances at the rate of computing. Meteorology largely does the same, with the added point that meteorology also advances one weather satellite at a time. And sometimes those advances do not occur in real time. To help us better predict the future, researchers regularly review data to see how what happened compares with what was predicted. During a review of the wintertime data on May 11, the National Hurricane Center retroactively determined that a mid-January storm that originated north of Bermuda was actually the first subtropical storm of 2023. This storm dumped snow on New England and gusted 60-mile-per-hour winds across Nova Scotia on January 16th. It turns out, sometimes when we say nor'easters look like winter storms, they are actually subtropical storms, which is weird. Normally, this storm would have received a name, but since its power wasn't recognized in January, It will remain nameless. The next storm to spin up will be a tropical storm labeled Tropical Storm 2 and will receive the name Arlene. After a break, we'll be back to look at earthquakes, ice ages, and underwater landslides. Stay tuned. Today, our world's average temperature is on the rise. Well, there are some places that will locally go down and some that will go up radically. On average, our world's temperature is going up a couple of degrees. This is leading to massive melting of sea ice and glaciers. Exactly what this will mean for people, especially for those living in coastal areas, is a hot research topic that has some scientists looking in unexpected places for answers. From the geologic record, including ice cores and sedimentary data, we know our planet has experienced a repeating cycle of ice ages and melts. The past handful of cycles went from ice age to ice age every 100,000 years, but earlier cycles, those that occurred more than 1,000,000 years ago, were only 40,000 years in length. To understand what we're learning from the land, researchers had to look to the stars. While current climate change is driven by the release of greenhouse gases into the air, past changes were due to how our planet receives sunlight and that change. We are essentially a very lumpy spinning top. As the Earth goes around the sun, it rotates about its tilted axis every day. Its axis rotates about every 26,000 years, and on even longer scales, the Earth's tilt varies from 22.1 to 24.5 degrees as the orbit's shape also changes from more to less circular. Right now, the Earth is closest to the sun in January, which causes the northern winter to be a bit more mild than the southern winter. New research published in Communications Earth and Environment with lead author Yusutu Watanabe used powerful computers to model the 100,000-year cycle from 1.6 to 1.2 million years ago to determine exactly what caused ice ages to end. And then they looked to see if those same effects could also explain the 40,000-year cycle that occurred more recently. They found that ice ages came to an end when the Earth's tilt was greatest and summer and winter solstices aligned just right with the Earth's orbit. According to researcher Takashi Ito, the numerical simulations performed in this study not only reproduce the Pleistocene glacial interglacial cycle, but also successfully explain the complex effects of how astronomical forcing drove the cycle at the time. We can regard this work as a starting point for the study of glacial cycles beyond the present-day Earth. End quote. It's all a cycle. A cycle that currently includes human-made greenhouse gases acting like an outside force, pushing the cycle to higher and higher highs, but it is still a cycle. And by studying what happened during the Earth's last great warming, we know what we can anticipate in the coming years. Case in point, in 2017, an ocean research vessel was studying the sub-ocean landscape off the coast of Antarctica when they discovered massive scarps and the remains of landslides that formed them. A year later, an additional research expedition collected core samples of the region. These core samples revealed layers of weak biologically rich material, including fossilized material, that had once defined the coasts. These layers were unable to hold up against earthquakes or other seismic activity, and instead collapsed, triggering massive underwater landslides that crushed material beneath while sending tsunamis through the oceans. These landslides occurred during the last great melting of glaciers and were likely triggered when shifting glaciers caused seismic tremors. Those scarps and landslides were discovered by study lead author Jenny Gales, who explains, quote, Submarine landslides are a major geohazard with the potential to trigger tsunamis that can lead to huge loss of life. The landslides can also destroy infrastructure, including subsea cables. This means future such events would create a wide range of economic and social impacts. Thanks to the exceptional preservation of the sediments beneath the sea floor, we have, for the first time, been able to show what caused these historical landslides in this region of Antarctica, and also to indicate the impact of such future events. Our findings highlight how we urgently need to enhance our understanding of how global climate change might influence the stability of these regions and the potential for future tsunamis. End quote. Put another way, we now know that melting glaciers can ultimately trigger underwater landslides. Those landslides can then trigger tsunamis, and those tsunamis won't be small. These events have historically occurred in both hemispheres and may ultimately be seen again both around Norway and Antarctica. This work appears in Nature Communications and is a reminder that we need to remain vigilant about how our landscape can shift right out from beneath us. The dangers of mid-ocean earthquakes and coastal landslides are highlighted every few months, it seems. Most recently, on May 18th, a 7.7 magnitude earthquake in the South Pacific triggered a tsunami warning for the Loyalty Islands and Vanuatu. When an earthquake strikes, the World Tsunami Alert Centers try to get out a tsunami warning within about 4 minutes. The decision to post an alert or not is based on earthquakes' locations and magnitudes. Unfortunately, when the most dangerous quakes occur, when our planet turns things up to 11, our seismographs don't always have the ability to go past 10. This means we sometimes don't actually know how strong a quake is until more distant sensors can process their weaker signals. This works, but it doesn't always work fast enough. Where one tool fails, switching tools can be the best option. In Alaska, where volcanoes and shifting tectonic plates drive regular seismic activity, researchers have gone from just feeling quakes to also listening for them. While seismographs measure the actual ground shaking, infrasound detectors can measure changes in air pressure caused by the ground's pressure waves shaking the atmosphere above. For the past several years, researchers have placed infrasound detectors next to seismometers to compare results. Where both instruments work, they get consistent results. And when the seismometers hit their limits, the infrasound monitor keeps working. This should improve tsunami warnings and ultimately help save lives along the world's coasts. This work is published in the Bulletin of the Seismological Society of America and was led by Kenneth McPherson. Today, there are 150 infrasound detectors throughout Alaska, and we can hope that more of these devices will be placed around the world. The Earth is a scary planet, but it is the most habitable place we currently have. We are getting better at understanding it. And with each new discovery, we hopefully can find more ways to protect ourselves and adapt to all the things our planet will send our way. Okay, that's enough of planet Earth. It is time to look outward to the regions beyond Uranus. Coming up next, correspondent Beth Johnson will be interviewing this year's Vera Rubin Award winner, Kat Volk, and discussing her work exploring the icy bodies of the Kuiper Belt. Stay tuned.
Thank you, Pamela. Planetary Science Institute senior scientist Catherine Volk was awarded the American Astronomical Society Division of Dynamical Astronomy's Vera Rubin Early Career Prize for her work on both the dynamics of small bodies beyond Neptune and the long-term dynamics and stability of tightly packed exoplanetary systems. Volk gave a presentation and received the award at the 54th Annual Division of Dynamical Astronomy meeting in Lansing, Michigan. Joining me now to talk about her award and research is Dr. Kat Volk. Thank you, Kat, for joining us today.
Thanks so much for having me.
So, Kat, what is the Vera Rubin Early Career Prize?
So it's a prize that the Division on Dynamical Astronomy gives out every year. It's relatively new. We used to only have a kind of an end career prize, and now the division added an early career prize maybe 5 years ago. And it's just a huge honor to be given that prize by my colleagues. And it's for recognition of research and service to the dynamical community and contributions to the dynamical community for researchers within the first 10 years since getting their PhD.
So, not to date you or anything, but when did you get your PhD?
Exactly 10 years ago.
Oh, wow.
Just within the 10-year limit. So,
That's fantastic. What's the process? Does someone have to nominate you, or how does it work?
yeah, so there's a nomination, like for many of the American Astronomical Society prizes. So a couple of my colleagues decided to support my nomination, and I believe there were 4 letters of recommendation that were written. And then for the early career prize, the nominee also writes a statement kind of detailing forward-looking research plans, how I plan to continue to contribute to the field of dynamical astronomy. Then all of that gets put into a nomination packet. It goes to the division. They have a committee that reviews all the nominations. Because it's a lot of work to put together a nomination, you're usually in the pool for a couple years, 3 usually, once your package is in. Except, you can time out of some of the early career prizes.
So, for the audience listening and viewing, what is dynamical astronomy? How is this separate from other parts of astronomy?
Yeah, so basically it is any kind of astronomy that has to do with orbits, orbiting bodies. So I do planetary system dynamics. So how planets or small bodies orbit their host stars. There are galactic dynamicists in the DDA, so people who study the dynamics of the stars in the galaxy and how they make interesting structures in galaxies, like bars at the center of galaxies. There are also some people who do dynamics around black holes. So basically, if it orbits, it can be part of DDA.
Thank you. That's fantastic. I'm very excited for you. So tell us obviously in your words, how this award felt, like what it meant, what it felt getting this award.
It meant a lot to me because the DDA is my favorite division. Sorry to the DPS. I love the planetary science community too, but I really love the DDA community. It's just really focused, and I always learn so much at the meetings. The meetings are a little bit smaller, although we've grown a lot in the last few years. When I started out, the meetings were usually about 60 people at the annual conference. So it's really an opportunity you got to talk to everybody who was there, as opposed to maybe a 1,000-person meeting where you only get to talk to a subset of people. So DDA is really special to me because my first conference that I ever went to was a DPS conference, and it was great, but it was huge and it was a little overwhelming. And then the next conference I went to was DDA, and it was just the smaller, closer knit community where I really got to talk to people and get to know people. And also just, I love orbits. So, every talk was great.
So, Kat, tell us a little bit about your history and your research. How did you end up doing planetary dynamics, and what has been your focus?
So I started out doing planetary dynamics because when I started grad school at the University of Arizona, Renu Malhotra had a project that was well suited to kind of a first year grad student looking at the dynamics of the scattering population in the Kuiper Belt. And so she hired me as a research associate to work on that project. And I just really fell in love with doing orbital dynamics. My background is physics, so it's kind of a natural fit for me. Sorry, excuse me. And so I really enjoyed that project and kept going with small body orbital dynamics. And then when I got my PhD, I moved on to a postdoc position with Brett Gladman at the University of British Columbia to branch a little bit more into the observational side of things. So I love being able to compare my models to observational data and really test them. And so he was running a big observational survey looking for new trans-Neptunian objects in the outer solar system Origins Survey. And that was really great to get better insights into the observational side of things. Brett is also a fabulous dynamicist, so he really does both observations and theory. And then, I just kind of kept going. And also when I was there, there were all of these new discoveries from the Kepler mission looking at multi-planet systems. So we started working on some investigations into the stability of these really closely packed planetary systems, because they're just weird compared to the solar system, where you pack all these planets so close together. You might have 5, 6, 7 planets in closer to their host star than Mercury, or at comparable distances. So It just looks really different, and you start to wonder, how can that be stable? Why don't these planets gravitationally perturb each other too much to maintain their orbits over long time scales? And I've continued some of that exoplanet work with Renu Malhotra, my PhD advisor, really looking into, when we do numerical simulations, we do see things kind of go into chaos and have planets on crossing orbits and kind of disintegrate the systems over time, and really looking at what causes that. This is not just kind of the proximity. So basically, how do you build a planetary system to be stable? And are all planetary systems truly stable, or are they what we call metastable? Like our own solar system might not be fully stable. There are long-term integrations that show you can have Mercury and Venus cause an instability that might or might not happen before the sun goes red giant. We're safe, it's okay. But there's a small chance that our solar system is not truly long-term stable. So there's just this interesting idea of, what is stability, what causes long-term stability. And it's a lot of the same concepts that go into the small body dynamics. So there's a lot of synergy between the two fields.
So again, just for the audience, can you really briefly explain what a trans-Neptunian object is?
Yeah, so it is a small icy body that orbits out past Neptune. So Neptune's the last major planet in our solar system. And, when the planets were forming, there were these disks of small bodies, the first things that formed, the smaller things that formed in the solar system. And the Trans-Neptunian objects are part of what's left over from that planetesimal disk in the early solar system that helped form the planets. So Neptune and the other giant planets formed in the what I call the inner part of the solar system, even though it's most people's outer part of the solar system. And they rearranged themselves, and Neptune is now 30 astronomical units from the sun. And in the process of rearranging themselves, they scattered out and implanted all of these small bodies into the trans-Neptunian populations out beyond Neptune. And we can use their current distribution and their physical properties, their chemical compositions, what little we can measure about them because they're very faint, to reconstruct what happened in the early solar system and figure out what's the history of our giant planets. How did they rearrange themselves? And then also just looking in detail at what the orbits are doing today, because it's not, the planets rearranged themselves, 4+ billion years ago. There's been other stuff that went on since then. So disentangling what's just long-term stuff that happened versus stuff that happened in the early solar system. And really combining that, we can model that and compare it to the observations. And our observational picture is really just starting for the outer solar system. We know of a couple thousand of these objects, which is very few compared to, for example, the asteroid belt. But what I'm really excited about in continuing to look at TNOs is that we're going to get maybe 10 or 40,000 of these objects when we have the Vera Rubin Observatory's LSST survey. When that comes online, we'll have a huge new inventory of objects to compare our models to.
That's going to be massive, and I'm very excited for all of the things named for Vera Rubin, apparently. When you gave your talk at the meeting in Lansing, what was the topic of your talk specifically?
So I chose to focus my talk on Neptune's orbital resonances in the Trans-Neptunian population. So DDA is a very orbit-friendly population of listeners, so you can get very technical with your talks, which is fun. You can show plots and equations that most audiences would kind of snore as a result of, but DDA will be excited about. So I talked about some of my recent research, really trying to figure out, how far does Neptune's influence go in the outer solar system? There's been some debates in the literature in the last 5 or 10 years about kind of what Neptune's region of influence is. And this is kind of related to like the Planet 9 debate, where are there some observed objects that are beyond Neptune's gravitational reach? And what we've shown in some of our research is that a lot of these objects that were thought to be beyond Neptune's reach really aren't, because the orbital resonances go out a lot farther than we would have thought. So I talked a little bit about the techniques we've been using to investigate that, and how some of our traditional intuition about orbital resonances is very different in the scattering population in the TNOs, because the orbits are extremely elongated. A lot of our intuition about dynamical concepts comes from studying mostly circular orbits, or things that are only elongated a little bit. But the TNO orbits are super elongated, so you have to kind of shift your thinking a little bit. So that is mostly what I talked about, and also because I think that's going to be really important for interpreting the new LSST observations. We really need to understand what the current dynamics of the solar system is, so that we can disentangle what was from the early solar system before we got to the current configuration, and what is just due to long-term dynamics of the current configuration.
So just for clarity, and again for the audience, can you explain a little bit about orbital resonances and what they are, and why they're important in what you're doing?
Yeah, so the orbital resonance most people are most familiar with is the Pluto-Neptune orbital resonance. So Pluto is in what we would call the 3-2 orbital resonance with Neptune. And that's because for every 3 orbits that Neptune goes around the sun, Pluto goes around the sun exactly twice. And the fact that there's that simple integer ratio between their orbital periods means that when Pluto comes to its closest point, so it's on an elongated orbit and it comes into perihelion, and that's when it gets the strongest gravitational interactions with all the planets in the solar system. When it does that, because of this orbital period ratio, Neptune is always in a repeating geometrical pattern with Neptune. So basically, Neptune's influence is kind of amplified, because Neptune is always either 90 degrees ahead or 90 degrees behind of Pluto when Pluto comes to perihelion. That's the stable configuration of that particular orbital resonance. It's not exactly 90. It does what we call librating around that. It's kind of like a pendulum that goes back and forth and librates around, pointing straight down. So there are all sorts of different orbital resonances in the trans-Neptunian space that extend out really far. And they're really important because when we observe the population, we see a lot of objects that when you measure their position, you measure their orbit, and you do a numerical integration, we find that they are doing a resonant libration with Neptune in many, many different resonances going out to, I think the most distant one is now the 20-1 orbital resonance with Neptune. So every 20 times Neptune goes around the sun, this object comes in and makes one orbit, and that creates a repeating geometric pattern. And these resonances are surprisingly populated, and that tells us if you were to just throw things down in the outer solar system, you wouldn't by chance end up with quite so many things in these resonances, because they only occur at specific distances to the sun. So it tells us that the resonances were filled probably while Neptune was moving, because that is when Neptune is migrating to its current orbit, you can fill the resonances and have them stick to those resonances long term. And that is an efficient way to add things to the resonances beyond what you would expect from just kind of randomly populating. So figuring out exactly what are the populations of all the distant resonances and what are the stable regions, because you can get into one of these resonances, but then leave because you didn't end up in a stable configuration. So we really need to understand, what do the resonances look like? They do stop at a certain distance from the sun because Neptune only has so much mass, it only has so much influence. So we have to understand, where do the resonances become important or not important, because it can also affect the long-term orbital changes of the objects.
So what's the future of your research? What are you working on now? What are you working on next?
So my next big project is actually a software development project, and it is to help people play in the sandbox of orbital dynamics. So with a couple collaborators, we got a grant from a NASA program to develop user-friendly Python-based dynamical analysis software. So the fact that rebound exists means, it's super easy to run numerical integrations now, which is awesome. But what's still missing is doing some of the analysis of those integrations. So, at scale, it can be very difficult. Like if you're just looking at one object, you can just look at the plots by eye and try to understand what's going on. You can run the integration, make pretty plots of the results. But when we're getting thousands of detections from LSST and we want to know what are the dynamically interesting objects, or just what is the dynamics of this particular object that was discovered, you need automated software that can analyze the integrations, figure out, is this thing in a resonance with one of the planets? Is its orbit rapidly changing, or is it relatively stable? And put it into the correct solar system population. Is it a classical Kuiper belt object, a resonant Kuiper belt object, a centaur, a Jupiter family comet, main belt asteroid? And again, these are all things that are easy to do on small scale by just people time looking at the integrations. But when you suddenly have, thousands and tens of thousands of objects to analyze, it becomes very difficult. So we are writing some software that will work with the rebound integrator to run integrations of observed objects and output some basic dynamical properties of those objects. And that we're hoping will help observers, pick from the 10,000 new LSST detections, what are the things they need to follow up on? If you see something that is showing cometary activity, that's interesting to follow up on, but there's limited telescope time. So you might not be able to follow up everything that has cometary activity. So you might want to follow up things that are in an unexpected dynamical class that isn't known to have cometary activity. So that's how dynamics can kind of interplay with the observational side to help, focus limited follow-up resources. But you need tools that make it easy to do that. Because right now everybody just kind of writes their own tools, and there's a lot of duplication of effort, and it results like I get a lot of emails asking like, can you run an integration on this object and tell me what it is? Like, yes, but like I'm going to give you software eventually that you can do it yourself.
That makes absolute sense. No sense reinventing the wheel, right?
Yep.
All right. Well, thank you for talking about all the science, and congratulations on your award. That is wonderful. I'm thrilled for you. We are all thrilled for you. On the personal front, can you introduce us to the little fur balls behind you?
Yes. So behind me, I have Gus and Echo. Gus is the tabby, who's just, yep, you heard your name. You're looking at it now. And Echo is the gray and white. They are my furry little research associates. And I did put their pictures in my presentation at the Lansing meeting, especially because we've had virtual meetings the last several years. So people have seen them in the background. So they're part of the research team now.
Absolutely, absolutely. They're our coworkers
Yeah.
down, and so where can people learn more about you, your science, and of course your cats? Because I know they actually have their own Twitter.
They do, yes. So I have a personal website that I link all my new science papers and anything else relative to my professional research. So catvolk.com. I'm also on Twitter, cat_Volk, and the cats are on Twitter. They're cats kitties. They also have an Instagram account that they have more followers than me because they're cuter than me. So you could definitely keep track of them on Twitter and Instagram. But yeah, best place to look at my research is my personal website. I try to keep that pretty up to date.
Fantastic. And we'll include the link to that in our show notes. So thank you so much. Thank you again, Kat, for being here with us today. And we look forward to speaking to you again on more research, because I'm sure there are more amazing things to come.
All right. Thank you so much for having me. Neptune's influence is kind of amplified because Neptune is always either 90 degrees ahead or 90 degrees behind of Pluto when Pluto comes to perihelion. That's the stable configuration of that particular orbital resonance. It's not exactly 90. It does what we call librating around that. It's kind of like a pendulum that goes back and forth and librates around, pointing straight down. So there are all sorts of different orbital resonances in the trans-Neptunian space that extend out really far. And they're really important because when we observe the population, we see a lot of objects that when you measure their position, you measure their orbit, and you do a numerical integration, we find that they are doing a resonant libration with Neptune in many, many different resonances going out to, I think the most distant one is now the 20 to 1 orbital resonance with Neptune. So every 20 times Neptune goes around the sun, this object comes in and makes one orbit, and that creates a repeating geometric pattern. And these resonances are surprisingly populated, and that tells us if you were to just throw things down in the outer solar system, you wouldn't by chance end up with quite so many things in these resonances because they only occur at specific distances to the sun. So it tells us that the resonances were filled probably while Neptune was moving, because that is when Neptune is migrating to its current orbit, you can fill the resonances and have them stick to those resonances long term. And that is an efficient way to add things to the resonances beyond what you would expect from just kind of randomly populating. So figuring out exactly what are the populations of all the distant resonances and what are the stable regions, because you can get into one of these resonances, but then leave because you didn't end up in a stable configuration. So we really need to understand what do the resonances look like. They do stop at a certain distance from the sun because Neptune only has so much mass, it only has so much influence. So we have to understand, where do the resonances become important or not important, because it can also affect the long-term orbital changes of the objects.
So what's the future of your research? What are you working on now? What are you working on next?
So my next big project is actually a software development project, and it is to help people play in the sandbox of orbital dynamics. So with a couple collaborators, we got a grant from a NASA program to develop user-friendly Python-based dynamical analysis software. So the fact that rebound exists means, it's super easy to run numerical integrations now, which is awesome. But what's still missing is doing some of the analysis of those integrations. So, at scale, it can be very difficult. Like if you're just looking at one object, you can just look at the plots by eye and try to understand what's going on. You can run the integration, make pretty plots of the results. But when we're getting thousands of detections from LSST and we want to know what are the dynamically interesting objects, or just what is the dynamics of this particular object that was discovered, you need automated software that can analyze the integrations, figure out, is this thing in a resonance with one of the planets? Is its orbit rapidly changing or is it relatively stable? And put it into the correct solar system population. Is it a classical Kuiper belt object, a resonant Kuiper belt object, a centaur, a Jupiter family comet, main belt asteroid? And again, these are all things that are easy to do on small scale by just people time looking at the integrations. But when you suddenly have, thousands and tens of thousands of objects to analyze, it becomes very difficult. So we are writing some software that will work with the rebound integrator to run integrations of observed objects and output some basic dynamical properties of those objects. And that we're hoping will help observers, pick from the 10,000 new LSST detections, what are the things they need to follow up on? If you see something that is showing cometary activity, that's interesting to follow up on, but there's limited telescope time. So you might not be able to follow up everything that has cometary activity. So you might want to follow up things that are in an unexpected dynamical class that isn't known to have cometary activity. So that's how dynamics can kind of interplay with the observational side to help, focus limited follow-up resources. But you need tools that make it easy to do that. Because right now everybody just kind of writes their own tools and there's a lot of duplication of effort, and it results like I get a lot of emails asking like, can you run an integration on this object and tell me what it is? Like, yes, but like I'm going to give you software eventually that you can do it yourself.
That makes absolute sense. No sense reinventing the wheel, right?
Yep.
All right. Well, thank you for talking about all the science, and congratulations on your award. That is wonderful. I'm thrilled for you. We are all thrilled for you. On the personal front, can you introduce us to the little fur balls behind you?
Yes. So behind me, I have Gus and Echo. Gus is the tabby, who's just, yep, you heard your name. You're looking at it now. And Echo is the gray and white. They are my furry little research associates. And I did put their pictures in my presentation at the Lansing meeting, especially because we've had virtual meetings the last several years. So people have seen them in the background. So they're part of the research team now.
Absolutely. They're our coworkers
Yeah.
down. And so where can people learn more about you, your science, and of course your cats? Because I know they actually have their own Twitter.
They do, yes. So I have a personal website that I link all my new science papers and anything else relative to my professional research. So catvolk.com. I'm also on Twitter, cat_Volk, and the cats are on Twitter. They're cats kitties. Um, they also have an Instagram account that they have more followers than me because they're cuter than me. So you could definitely keep track of them on Twitter and Instagram. But yeah, best place to look at my research is my personal website. I try to keep that pretty up to date.
Fantastic. And we'll include the link to that in our show notes. So thank you so much. Thank you again, Kat, for being here with us today. And we look forward to speaking to you again on more research because I'm sure there are more amazing things to come.
All right. Thank you so much for having me.
This week is rather special in that we have a rare trio of crewed space flights to cover. It all started on May 21st with the Axiom Mission 2 launching on SpaceX's Crew Dragon Freedom. On board were 3 aerospace professionals from Axiom Space and the Saudi Space Commission, as well as a paying tourist. Together, they'd spend 10 days running science experiments on the International Space Station. The mission was commanded by Axiom's Peggy Whitson, a former NASA astronaut and the first woman to command the International Space Station. She holds the record for most spacewalks by a woman and held the record for the longest spaceflight by a woman until 2020. This flight made her the oldest woman to orbit the Earth. Joining her were Ali Al-Khanari and Renea Barnaway, the second Saudi man and first Saudi woman, respectively, to travel in space. Ali is a pilot in the Saudi Air Force, while Renayan is a biologist who studies cancer stem cells. Rounding out the crew was John Schaffner, an experienced pilot with almost 9,000 hours logged in everything from commercial airlines to fighter aircraft. He was also very successful in the fiber optic internet industry during the 1990s. The crew performed experiments ranging from how certain enzymes affect cancer spread to mRNA research on inflammation. They also brought art made by students and made amateur radio contacts with members of the public. Crew Dragon Freedom successfully returned to the Earth on May 30th, closing out the second private mission to the International Space Station. From a commercial capsule, we now turn to a commercial not capsule. Badminton, Birdie? On May 25th, the Virgin Galactic Spaceship Two VSS Unity performed its first suborbital flight in almost 2 years. Joining the mission's 2 pilots was a crew of 4 Virgin Galactic employees, 3 who were flying into space for the first time. The 1-hour flight was completed nominally, with the space plane and its carrier taking off from Spaceport America, New Mexico. The time in space was only about 15 minutes, and it only reached an altitude of 87.2 kilometers. This was over the 50-mile altitude NASA and the FAA used to define space, but under the Kármán line of 100 kilometers that is considered to be space by most of the rest of the world, which uses metric. The 2-year lag between flights allowed the FAA to investigate an earlier launch that went off course and temporarily entered unrestricted airspace on reentry without clearance. The pilots would normally have aborted the rocket burn on ascent to keep the vehicle in their restricted airspace, but they failed to do so because cutting the rocket would have caused company founder Richard Branson, who was on board, to miss out on becoming the first space company CEO to ride his own rocket into space. He did this a week before a similar attempt by Jeff Bezos, founder of Blue Origin. Virgin also took this time while grounded to fix problems revealed on that first flight. The last crewed space flight in the last week was China's Shenzhou 16, which launched atop a Long March 2F on May 30th. On board were 3 taikonauts, including specialist Guo Haiqiu, China's first civilian astronaut. The other crew members were Commander Jing Haipeng, who's a veteran of 3 previous space flights, and Flight Engineer Zhu Yangzhu, who is the first astronaut of China's 2020 astronaut class to fly. Both are Chinese Army officers. Shenzhou 16 docked with Tiangong a few hours later, making it the 4th crewed mission to the Chinese space station. The crew will spend about 6 months in space, conducting various experiments and several spacewalks. And now, to cover this week's uncrewed missions, I'm pleased to welcome on aerospace correspondent Eric Mattis for this week's Tales from the Launchpad. Hey, Eric.
Hi, Pamela. There were too many uncrewed launches to cover in the show this week, so we've decided to mention just the more notable ones. The third KSLV-2 was launched on May 24th from the Naro Space Center in South Korea, carrying several small satellites for KARI, the Korean Airspace Research Institute. The primary payload was NextSat-2, a radar imaging satellite. The other 7 satellites consisted of 4 small astronomy satellites for KARI and 3 CubeSats for different commercial customers. Rocket Lab launched the final pair of Tropic satellites for NASA on the Coming to a Storm Near You mission on May 26th. This flight was conducted from the second of 2 pads at their New Zealand launch site on the Mahia Peninsula, just 17 days after the previous Tropics mission. The Indian Space Research Organization, ISRO, launched another satellite in their Regional Navigation System, IRNSS-1J, on a GSLV Mark II rocket from the Satish Dhawan Space Center on May 28th. It's the 9th satellite in the constellation and is a major improvement on the first generation, with clocks built in India and a new civilian signal. As well, there were another 2 batches of Starlink satellites successfully launched on May 19th and 30th. And there was one additional attempt to launch from an unexpected corner, but I'm going to leave that to you.
Thanks, Eric. Finally, we have one last launch to talk about. On May 30th, at about 21:30 UTC, North Korea made its 6th attempt to launch a satellite, the first since 2016. According to reports from the state news agency, KCNA, the Cholima-1 rocket failed due to an abnormal startup of the engine on the 2nd stage, after the first stage separation. Had it been successful, it would have put Malayang-1, the country's first spy satellite and 3rd satellite overall, into orbit. The rocket, which used ballistic missile technology, was expected to fly south over the Yellow Sea and then the Pacific Ocean, with stages and other debris falling into the water along the way. Instead, the launch attempt triggered air raid sirens in Seoul and emergency alerts, and even evacuation warnings for a short period of time in parts of South Korea and Japan before they were canceled. There were no reports of damage from debris from the launch. Not surprisingly, this failed launch drew strong condemnation from the United States, Japan, and South Korea, who have all said they will stay vigilant with a high sense of urgency. The United Nations Secretary General Antonio Guterres also spoke out against the launch, saying Pyongyang using ballistic missile technology was contrary to UN Security Council resolutions banning it from conducting any launch using that technology. According to KCNA, Pyongyang's National Aerospace Development Administration will look into the serious defects and attempt to resolve them as soon as possible before making a second launch attempt. South Korean officials have said there is a good chance of another launch attempt before June 11th, based on a 12-day notification North Korea made to the International Maritime Organization. Pieces of the launch vehicle and its payload have been retrieved from the ocean by the South Korean military. This brought us a new list for stats this week. We keep track of orbital launches by launch site, also called spaceport. According to Rocket Launch Live, so far this year, the USA has had 40 launches, China 19, Kazakhstan 5, India 4, New Zealand 3, Japan and Russia each have had 2, and French Guiana, Israel, North Korea, South Korea, and the United Kingdom each have had 1. Of these 80 launches, there have been 5 failures, reminding us space is hard. Before we go, I just want to take a moment to emphasize 3 different organizations launched 3 different groups of humans into space last week. While folks may debate if Virgin Galactic's flight counts as making it all the way to space, I think everyone can acknowledge these were 3 flights that launched above the sky and saw our world as a round planet. As more companies bring human launch capabilities to more places, we will see this happening more and more. We are at a transition point in human history where it's about to become normal for the extremely wealthy to leave our planet and sometimes take the lucky scientist along with them. While I can't always promise tourist flights will carry scientists, I can promise the multi-day missions will carry space toilets. For just the second time, there were 11 space toilets in orbit for astronauts to use. 4 on the ISS, 1 on Soyuz MS-23, 1 on Crew Dragon Endeavour, 1 on Crew Dragon Freedom, 2 on Tiangong, 1 on Shenzhou 15, and 1 on Shenzhou 16. There is actually a much better ratio of humans to toilets in space than here on Earth. There is also a lot less privacy in space. Balance that how you will. That's it for now. Good night, everyone, and remember, go look up.